Why hello there airplane design buddies. Today I'll be going over a brief introduction on electrified aircraft propulsion. Why do people want this? Well, airplanes are not very environmentally friendly, also fuel costs money, and it'd be nice to know what it takes to electrify planes in general, and what effect that will have on our national airspace, and also everyone's talking about it. But this is an aircraft design video, not business, so let's talk about the batteries. So the batteries weigh a lot. Let's look at a case study. So Magniacs had their Eco Caravan in 2020. So they put their EPUs on it, so I might have gone the make wrong, but they took this Cessna Grand Caravan, and then they put like a ton of batteries on that. Okay, batteries aside, when you add extra weight to a plane, you increase the fuel consumption and reduce the overall performance. Range will take a hit. Again, I said that's for conventional aircraft, not necessarily, the battery-powered ones, but you get what I mean. If you take a screenshot there, it's going to make me look bad. But anyways, conventional fuel-based aircraft propulsion systems, they kind of look like this. You got your fuel, your turbine, your propulsors, and by the way, when I say SE, that's specific energy. Also, all these components have their own efficiencies. This is supposed to be a 5-minute video, so I'm just trying to keep it as simple as possible. But let's also look at, turbo-electric aircraft propulsion systems. So a lot of people, they get that mistaken with EAP. I hear them use it interchangeably. But turbo-electric is like, gas turbine generates electricity to the power electric motors that are driving the EAP system, and that's a part of EAP systems, but it's not synonymous. And as you can see, it has this electric drive system with electric efficiency. And now let's talk about another system we see a lot in the wild, and that's the parallel hybrid electric propulsion system. So as you can see, I'm introducing to you a new squiggly. This is zeta, and that is electric propulsion fraction, aka the fraction of the total aircraft thrust produced by the electric-driven propulsors at cruise. We got two different forms of power storage. That's the fuel, the battery, and of course we got this electric drive system. And as you can see, when squiggly equals 1, all thrust is produced by electrically driven propellers. For the turbo-electric, all the thrust comes from, electrically driven systems. And the limiting reagent for these recipes is something called battery-specific energy density. Say that to scare any engineer working with electric systems. So I know there are not a lot of believers in electrified aircraft propulsion. I mean, even I, of all people, had my doubts, and I've worked at basically electric car company, electric plane company, and now I work at NASA. I can't say my opinions out loud, but I wrote them out there. So for all the configurations shown, we want to think about the component efficiency. So what are the building blocks here? We have our energy source, that's fuel or battery, turbine engine, propulsor, electric drive for EAP, and these all come with their associated efficiencies. So I learned about propulsion like this, the inlet, suck, squeeze, bang, and push. Okay, I know it's kind of awkward, but it's always helped me remember that, and also what T4 temperatures are. So the fuel power, battery power, turbine power, electrical power, and propulsive power, all in kilowatts, are defined as the output power. And here I'm going to show you the overall efficiency of each aircraft type as functions of propulsive, thermal, and electric drive efficiency. Oh snap, I think I forgot one system, so that's partially turbo-electric. This is how it looks like, so don't make you try to imagine it. This whole drawing thing is kind of hard. I'm trying to figure out how to make my videos a little easier here, but anyways, that's the equation, and that's plus squiggly. I think I forgot to do that. Anyways, so we're back to the Breguet range equation for fuel-based aircraft, which I've made a video on if you want to go look at that. BSFC is the brake-specific fuel consumption, and I'll show you how that is calculated in terms of specific energy of the fuel, and then now you get this form. So compared to battery-based aircraft, R battery equals specific energy of the battery over G times L over D. You see the equation. So then we can see that, for small values of W fuel over WI, I guess it's pretty similar. So yeah, look at those equations. It took me about 4 minutes to get to them. Anyways, since the specific energy of the battery is much less than the specific energy of the fuel, the battery weight for the same range will be much larger than fuel weight. Also, feel free to pause if this is going too fast. Anyways, so the input energy of fuel is simply the product of the specific energy of the fuel and the fuel mass. If you have my job, you're going to have to do trade studies to kind of show, like explore the design space. Aircraft range is approximately proportional to the weight of the electric drive over the weight of, the complete system. And then you want to do that in terms of, the battery drive specific power. Also, the efficiencies are important. So again, based on what your target performance is, you'll be looking at these break-even points where, you want to figure out, I guess, efficiency here in terms of range, weight ratios, and specific power. You end up finding that parallel hybrid electric aircraft is better suited for shorter range operations, and also improving battery-specific energy will just make all of these configurations way more feasible. So yeah, I hope I was able to kind of present this topic to you in 5 minutes.